So, all right, so chapter 16 is about integration of 2 and 3 dimensional functions, functions 2 variables and 3 variables. And we've done 2-dimensional and 3-dimensional iterated integrals. And now in the next two chapters, we're going to consider doing integration in alternative or non-Cartesian coordinate systems. And I want to do there's always a danger in this stuff that one can get really bogged down, because as I've already seen triple integrals, it's almost like you're doing 3 integrals at once. It takes a long time, right? And so I'm going to try to not do a lot of super difficult or involved examples. There'll be a few. But this is a pretty common technique, and it's a very useful technique. So let's start by going back to thinking about rabbits. And so let's say we have rabbit density. And that's xy, and that might have units of rabbits per meter squared. And then if we have some region so we would take rabbit density and we multiply that by some little area. We've done this a bunch. Rabbits per meter squared times meter squared give you rabbits. You add up all of those, and you get the total number of rabbits, and that's what this quantity represents. And you've done this with numbers, and you've done this with values in a table or on a contour map of some sort. And my impression is, comfortable might be too strong a word, but are starting to feel okay about this. Right, so a few people are agreeing, perhaps out of politeness. But now let's imagine that again we've got rabbits, and it's a non-uniform distribution, but maybe the rabbits happen to be, these are densities. Probably didn't need to write quite so many numbers, but I got them all. So when we evaluated these in Cartesian coordinates, we said I could add up all the rabbits this way, or I could add up all the rabbits this way, and it's the same number of rabbits. And now suppose the rabbits were in this sort of funny pattern. So maybe there's something bad for rabbits here. A fox, a rabbit-eating creature. And so, there's going to be more rabbits farther away, and really all that matters for the rabbit population is how far you are from the origin where something bad is. I mean, it could happen. Right, in physics, if this was a negative charge or something, your electric field matters only, depends only on how far you are from that charge. And so it's going to be the same in a circle all the way around here. It's going to be the same in a circle all the way around here, and so on. So if you had to do rabbit censusing here, you say, okay, I know I have the freedom to choose, let's do the y first, or let's do the x first. But again, you might think, actually it would be a lot easier. I'd actually like to count circularly. Because if I just go around in a band like this, I can't do that. Then that's really easy, counting up the same number all the time. And then I could count in this band and count all of those up as well. And of course, if you're just counting rabbits, counting them isn't really that hard. But remember, this actually would be an integral, and so this would mean you're integrating something that's a constant, and those are really fun integrals to do compared to other integrals. So what I'm trying to suggest is that sometimes it will be convenient, which is shorthand, which you probably know in math means somebody's about to do something that seems very inconvenient. But anyway, it will be convenient to integrate in polar coordinates, i.e. in circles, as opposed to in straight lines. Okay, so let me do a little bit of geometry to set this up, and then I will probably do a quick example, and then you guys can do examples probably to see how this goes. So first, just a reminder about polar coordinates. Right, so here's a point in space, and we could specify it by an x value and a y value. And those two numbers uniquely determine the point in space. That tells you where you are. But you could also specify that point in space by giving this value, the radius, r. So this tells you how far you are from the origin, and then theta would give you a direction. And those are both perfectly legitimate ways of specifying a point in space. And if you tell me r and theta, you're giving me polar coordinates, and if you tell me x and y, you're giving Cartesian coordinates. And unlike human languages, it's possible to translate with absolute certainty from one language to the other. X is so we can get x and y using right triangle trigonometry. Let's see, what will r be? How's r related to x and y? And what about theta? If I tell you x and y, what would you need to do to figure out theta? This is y. So that's opposite of r. So I think of this as like a bilingual dictionary. This says, you tell me x and y, I can convert that to r and theta. This says, you tell me r and theta, I can convert that to x and y. Okay. So now, let me remind you of one other fact about angles, and then we'll start I'm going to set an integral. If this is theta, this is r, what's this curvy arc length? Usually S. So we get like due process of the limit. So S is going to have units of length, right? So, like, I shouldn't divide by r because then the units would be wrong. So, like, I'm going to have to put an r there. R theta, yeah. S equals r theta. It's one of those short little phrases that gets stuck in our heads. So the way I sort of remember this or think of this is actually that this is a definition of what it means to be an angle. So like the different ways of measuring an angle. We could measure it in degrees, and that's sort of, on the one hand, reassuring because most of us grew up measuring angles in degrees, but it's sort of a drag because the way it's like 360 degrees. You know, who decided that? It's just some dumb arbitrary thing. It's probably the Babylonians, because lots of things divide into 360. Right, 3, 4, 5, 10, 12. So,
isn't that in radians though?
yes, exactly. So this is only true in radians. And so this relationship I think of as defining what a radian is. It's a way of measuring an angle. And if we don't want to still worship the Babylonians, we could say, well, why don't I just take the ratio of this length, this is S, to R. The bigger S is, for a given R, the bigger an angle it is. And because I'm an American, I could choose to do this in miles or inches, and it doesn't matter. And if some of you are feeling anti-American or not from America, you could do kilometers or light years or whatever. It doesn't matter. We're all going to get the same number. So it's independent of units. It's a rate. Right? It doesn't matter what human conventions we use for this. We get the same number here. Okay. So this is going to be a useful fact. Probably somewhere in like. Not as useful as patience, maybe even more useful than parentheses, hard to say. But, all right, so now let's get ready to think about how we would set up one of these intervals in polar coordinates that I claim will be convenient. All right, so we're going to use this. And I need to think about what the area element would be if I'm adding up in these funny little circles. All right. So here's the picture. This would be one little step, one little delta A, as I'm adding up all the rabbits in a circle like this. And because we're given the density, we always need to do density times area, density times area, density times area. So we need to know what the area is. So the question is, what is the area of this funny little thing that's a rectangle, but actually not quite a rectangle?
Inner S and outer S.
Let's see, so this, I'm going to call this dr. That would be a step in the radial direction away from the center where the fox den of foxes?
Yeah.
Sure, fox den is, or the electric charge or whatever it is. So then this length, I want to know what's this length?
R.
It's an S, so it's I claim this is going to be R theta. So this this little angle here, which I couldn't quite fit in.
Oh, that's delta.
That's a delta theta, yeah.
So
it's
what's theta? Theta.
Theta is
The outer one. For some reason I thought you were deriving the angle.
That is the whole thing?
Theta is just up to
Okay,
the.
yeah.
Yeah, there we go, that's a better diagram.
So
Yeah.
in this diagram, you're super zoomed in, is that what it is?
Yeah. Because it's a delta.
Yeah.
It's a delta.
Yeah,
just
these
one
are,
part.
these are small, yeah.
Okay.
And so this is, so we don't have to think about it too much in Cartesian coordinates because like all the rectangles are the same size.
So then R goes from the origin to where dr starts.
Yeah, this is R. Yeah. So, moral of the story is, that when we're counting up rabbits, we always need the area. Because we have density, rabbits per square meter. And this is the size of each little kind of rectangle of area, but it's no longer constant. So that's the thing that's weird. And that's why I still need to assert, it will be convenient. Future tense. It may not seem convenient now, but it will be convenient. And so a way to think about that is, suppose you and your friend are both taking part in the rabbit census in this funny circular way. And I'm gonna should I write on top of this diagram? Or do you want me to try to do it? On top of the diagram? Okay.
No.
No, okay. So, all right, so one of you is gonna so are going to sort of sweep out a path this way, are going to sweep out a path that way. And what you decide is you're each going to move 10 degrees, however many radians that is each time. You decide on what your delta theta is going to be, and you each decide, all right, I'm going to take a meter on the left and the right, or something like that. So you're going to kind of go, okay, how much of that is, how much of that, how much of that. And let's see if I can. I guess I'll just do. So this is the first theta that you take. And so you take 10 degrees, step forward, and see what's going on. And your friend takes 10 degrees, step forward, and then you compare notes, and you're like, hey, my area is bigger. Right? So this person's going to have a bigger area because her R is bigger. And you can just kind of see it on the diagram. So that's another way, right, what I'm trying to suggest is that the little rectangle, the area, is actually no longer a constant. It depends on R. It's a bigger area if you're farther away. All right. Let me do an example, and then I think I will finally be done talking for a while. All right. what's an example? So let's have the rabbit density be a constant. We could choose a letter, we could choose a number, what do you feel like?
You're gonna use
Putting
X.
C.
C, we're gonna call it C, okay. Density C. So the region, let's have it be a circle of radius 10. That's probably a number. All right, so usual question, how many rabbits? Okay, so already some of you are perhaps reflexively, maybe reflexively and reflectively, thinking, okay, Pythagoras, this is going to be 100 minus x squared, the limits are going to be a pain, and we're going to have square roots to plug in. Those days are behind you. So we're going to have an r dr d theta, and we're integrating just the number 10. And if I want to sweep out this space, what does r go from? Starts at 0,
0 to 10.
and it goes 0 to 10, yeah. And then what do my angles need to be to sweep out the entire circle?
0 to 90. No, 360.
360, but we love radians, so it is
5 to 5.
yeah. And in fact, not only is it a matter of the fact that we love radians, this forces us to use radians. Because this relationship is only true in radians. All right, so now we can just do the integral. Antiderivative of r with respect to r. So this is going to be 10r squared on 2, 0 to 2 pi. R is going to go from 0 to 100. Oh, sorry, 0 to 10. So let's see what's going to happen here. This is going to be 10 cubed, which is 1,000.
That's where it is. You're fine.
Oh, then by then.
You're fine.
Oh.
Okay.
That's
Yep.
correct.
Sorry, yeah. Actually, oh,
No.
okay, what's the antiderivative of all this with respect to theta?
500 here.
So yeah, this comes to 500, the 1,000 over 2.
Theta.
And then this is just theta divided from 0 to 2 pi, which is going to be 2 pi times 500, which is 1,000. But why did I use 10 for the density? There's no answer to that question.
Yeah, this,
The density was C. I was so surprised you guys chose a letter. I thought you would choose a number. Like, let's do 7 or 13 are my favorite number, but, all right, so,
Oh, you don't have.
Or you could just change the other.
that's true, yeah,
Just keep
good
it
point.
10. Sorry, I chose a letter.
No, I mean, that was good, I was just.
Yeah.
It's a good idea.
Just wanted to encourage us to practice some algebra.
Okay, so you didn't really need to use an integral to do this because it was a constant. We need to do integrals when we're adding up something that's changing when we're adding it. Here, it's a constant, it's not changing when we're adding it. If the rabbit density is 10, and you want to know how many, everywhere, and you want to know how many rabbits there are, you'll just do 10 times the area. You know the area of a circle is pi r squared. And so that's what we found here. So this is probably the quickest derivation for the formula for the area of a circle. We did an integral without having to deal with any of those annoying square roots. So perhaps you now believe me when I say it will be useful sometimes to do integrals in polar coordinates. It's useful when you have a situation like the rabbit example before, when there was circular symmetry. It's also useful when the shape you're integrating is a circle. All right, let's do some integrals.
Can you do it in another way that it's not a circle?
Yes. So this one's is a circle of radius 7. So it's similar to this one, except now this is 7. So as we can imagine like sort of counting circularly, or you could also imagine you're going to count radially first. But you can imagine you and all of your rabbit counting comrades all start at the origin and are going to fan out in different directions. So you're counting this way first. So radially, in terms of the radius, you need to go from 0 to 7. And then you need to do that all the way around the circle. That's from 0 to pi, all the way up to 2 pi. So that gives me these limits. The next two are for the unit circle, so the radius is just 1. We're going from 0 to 1. If I want the top half, I'm going to start at theta equals 0 and go around to theta equals pi. If I want the left half, which is what I've shaded here, I'm going to start here, 90 degrees, which is pi over 2, down to 3 pi over 2.
What if you wanted the right half? Like, because you would have to go from like half pi to...
You could do minus pi over 2 to plus pi
Okay.
over 2,
Yeah.
probably would be how I would set that up.
Yeah.
And then here, the flat donut thing. Okay, clearly not to scale, but I haven't stopped us before. So R is going to start from one end at 3, and then you need to do that all the way around the shape, hence that. So let's do the following. Let's do problem 2C, and then see if we can get through problem 3. And if we can't, we'll finish it up next time. So here's the integral in polar. Here's the shape. It's the left half unit circle, and we want to write it in Cartesian coordinates. So we have a choice. We could do x first or y first. I thought, well, let's try both. So if I'm doing x first, I'm going to add up the rabbits in this direction. So then I'm always going to stop when I get to 0. But my lower limit is going to depend on y, what my altitude is. So my upper limit for this one is always 0. My lower limit depends on y. And so it'll be the negative root of that. It'll be negative 1 minus y squared. So then once you do this integral, you're going to have y's left over, but that's okay, because then you're going to do a y integral from -1 to +1. could also say, well, this doesn't look like fun. What maybe it's more fun in the other direction? Then you would say, all right, I'm going to add them up in the y direction first. So that means I'm going to go from the minus to the plus. What's my y value as a function of x, right? Because different, where I am on the x-axis is going to have different starting and ending points. So that's going to be minus 1 minus squared plus 1 minus x squared. And, all right, that's my y. And then my x's are going to go just from minus 1 to 0. So it would depend on what the particular function was you were integrating, but odds are this is going to be a lot nicer to do than that for this. Because if it ever happens, you're going to get an x and you're going to need to plug in the square root, and that can be bad.
If we didn't know nothing.
So far I've only talked about how to set up intervals. We also need to think about how to actually do a few intervals. And the trick there is we often start in Cartesian, but then if we want to do an integral in polar coordinates because it will be convenient, we need to convert everything into polar. You need it to be in all one language or all the other. And so that's for the two problems for part 3 will give us some practice doing that. So let's give those a try and then we'll definitely wrap it up. All right, so the area we're integrating over is the upper right quarter of this flat donut annulacy thing. So the limits are the same as those that we had before. For this one, 1 over x squared plus y squared is 1 over r squared. Be careful not to forget the r d theta. This r that's in the r d theta, which is part of dA, is actually an r. It's not just sort of like something you need to write. So that's why this 1 over r squared became 1 over r. And then antiderivative of 1 over r is log r, and then one should end up with that, I believe. So certainly much nicer than trying to do this in Cartesian coordinates. This would be bad news to do in Cartesian coordinates. Now imagine we're trying to integrate this function, just the function y. And so it might not be immediately obvious, should we do Cartesian, should we do polar, but well, the chapter is polar, and the area, I mean the shape is polar, so the limits are going to be much more nice if we do polar. So we're going to have to take y and we convert that, we translate that into polar, and y is r sine theta. So look that up in our bilingual dictionary, boom, there it is. And we're happy. So this is not quite as nice a function as y, but it's not going to be that difficult to integrate either. The area element is r d theta. Remember the r is a real r, not just a window dressing r. And if one does this, one ends up with 26 over 3. And if you took this answer and you divided it by the area of this, which you'll need to do another integral to get, you would get the y coordinate of the center of mass of this shape. So basically you're averaging y over the area. If you take y and divide it by the total area, you have the average value of the y, and that would be the y coordinate of the center of mass. So in sort of simple statics mechanics, when one's calculating the center of masses over weird shapes, one has intervals like this all the time. So we'll do at least one more example, maybe 2 in class tomorrow, and then we'll do spherical coordinates, which will make polar coordinates look flat and simple.
Are you running away or are you going to
I'll be up in tab for the next like 10 or 15 minutes.